This video is brought to you by FlexiSpot. Hi guys, welcome to Amateur Chemistry. So we probably all know opals. These precious stones are among the prettiest and most sought after gems there are, all due to their characteristic play of color and hundreds of types to choose from. I mean, I fell in love with them at first sight, and ever since I was just fascinated by these weird color-changing rocks. A while ago I actually bought some just to see what they are like in real life, and even though they are relatively small and low grade, they are just gorgeous. They were actually quite cheap gemstone-wise, which was a nice surprise. However, the really pretty opals can sell for hundreds of thousands of dollars. Now you may ask, why the hell am I talking about shiny rocks on a chemistry channel? And for pretty much all the other shiny rocks, this is quite a valid question. Opals, however, are quite unique in that they can actually be made. You see, they are completely unlike other gemstones because while most get their color from some rare metals embedded in them, the beauty of opal actually comes from its structure rather than what it's made of. Ruby, for example, has a brilliant red color due to a tiny amount of chromium embedded in its aluminum oxide matrix, while most opal is basically made out of extra fancy sand. Sand is made from something called silicon dioxide, and while in things like glass it takes the form of an unorganized mess, in opal it forms tiny, highly ordered spheres that are colorless by themselves, but together can stack and reflect light in a way that produces all these colorful flashes. Now, it turns out that there exist some ways to create such tiny grains of sand and use them to make what's known as synthetic opal, which can be even more beautiful and diverse than the real stuff. Upon learning about this a few years ago, I became more than hooked and dreamed of one day making some opals myself. During these few years, I gradually became more chemically advanced with many new experiences and equipment available to me, which is why almost precisely a year ago I decided it's time to cook up some homemade opal. Now, while doing this using store-bought chemicals would already be a big feat, what makes this project even better is that after a lot of research, I figured that it's possible to produce opals starting directly from sand. This kind of alchemy-like process is the pinnacle of what I aim to showcase on this channel, and with a lot of hope and not really knowing what I am getting into, I started this project. Now, looking back at this nearly a year later, I just can't fathom how much blood, sweat and tears I poured into this project, making it the longest, most frustrating thing I've ever done for a video. Before I show you the colossal journey of making my own gemstones from the literal ground, I want to introduce you to a better way of working, or in other words, this video's sponsor, FlexiSpot. You see, making my videos requires dozens of hours of editing and script writing, which up to this point I did behind this old crappy desk. As you can see, it's far from perfect, being really wobbly and forcing me to sit on my chair for hours on end, which is why I recently decided to get healthier and find a good standing desk. Now, while there are hundreds of regular standing desks to choose from, none of them really fit my needs, and I honestly kind of lost hope in them until I stumbled upon FlexiSpot. Their standing desks really are state of the art, and they've been kind enough to send me their new E7 Plus desk, which is honestly just perfect, and it feels good to say that and actually mean it. I had an amazing time with it from the moment it arrived, since even setting it up was a walk in the park. It took me only an hour to do and was weirdly straightforward for such a big desk, and when I was done, the amazement didn't stop there. You see, the best thing about this desk is that you can precisely adjust its height with a push of a button, and it's so stable that even at its max height of 130 centimeters, it pretty much doesn't wobble. Its monstrous 4-leg design, coupled with 2 electric motors, makes it operate incredibly smoothly and silently, and even my cat, who really doesn't like being disturbed when she eats, doesn't even notice its movement. It also automatically prevents accidents by stopping the motors when it detects any obstructions, which is just a chef's kiss. The robust build also makes this desk able to carry gigantic loads of up to 200 kilograms, and all the gym equipment I have along with me is nothing for it. What makes this desk even cooler is this array of buttons along with a precise height display screen, which apart from giving you complete control over the desk's height, allows for up to 4 programmed positions. This makes me able to go from working in a chair to using a standing desk with a single button press, making this whole thing even more convenient. Thanks to FlexiSpot, I can now make videos while not actively destroying my back, and if you want to buy a standing desk or any other product from FlexiSpot's diverse offer, visit flexispot.pl or use my link in the description, and big thanks to FlexiSpot for sponsoring this video. Anyway, in order to make homemade opal, I first need to figure out how to create the unimaginably tiny grains of sand that make up its structure. I have to make them in just the right size to achieve the play of color effect, and this is where everything gets really tricky. Since I want to ultimately make them from sand, the first thing that comes to mind is just grinding it until its particles reach the desired size, but in reality I need a way more controlled and precise approach. Basically, the only option is to use some silicon-containing chemical and turn it into silicon dioxide chemically, which when done just right, allows me to freely adjust the size of my tiny spheres, controlling the properties of the final opal. This adds another step to my sand to opals process, and I now have to figure out what chemical I have to turn sand into. Now, the most popular and pretty much only viable one used for this kind of thing is this bulky boy called Tetraethyl orthosilicate, or TEOS for short. It both contains silicon in a pretty reactive form and is a liquid, making it the perfect thing to controllably turn into silicon dioxide. Unfortunately, it is a chemical hell to make yourself, even with store-bought ingredients, and making it from sand is another level of pain. I nonetheless decided to do it, both since it would be hella cool and because literally nobody sells such an exotic chemical to private individuals. Now, there isn't much information online on how to make TEOS, and the easiest method with an OK yield seems to be reacting ethanol with something called silicon tetrachloride. The ethanol part of this is quite easy, since it's a very common laboratory reagent. The silicon tetrachloride part, however, is where it gets bad. Silicon tetrachloride is actually one of the worst chemicals in existence, since it reacts with water in your lungs and eyes to make sand, and making it is excruciatingly painful. On that I speak from experience, since this video is actually the third installment in my Opals from Dirt series, from which the previous 2 videos led up to making silicon tetrachloride. After going through chemical hell, I actually succeeded in making a small amount of it from some sandy dirt I collected in my backyard, and if you want to see the whole process covered in detail, you can watch those 2 videos. In a nutshell, to start turning natural silicon dioxide into silicon dioxide but fancier, I first extracted some pure sand from dirt, turned it into elemental silicon using a very fiery and toxic process, to then react it with chlorine gas in a mad scientist apparatus, making this small vial of silicon tetrachloride. In theory, I could now directly go to turning my silicon tetrachloride into TEOS, but since I don't even have 20 grams of it, I was feeling quite pessimistic about how much opal I would end up with. Even though making silicon tetrachloride is the most annoying chemical process I've ever done, I decided that if I take this project seriously, I have to make some more, and since I still had quite a bit of homemade silicon left over, I won't have to repeat all the dirty work. I also have quite a few ideas to improve on pretty much everything from my previous video, and the first one was to better grind the silicon. You see, to make its reaction with chlorine go smoothly, it has to be really finely powdered, and the last time it definitely wasn't. It's all due to me using this coffee grinder, which is just trash, and for this run I decided to deploy my homemade ball mill. Its heavy-duty steel balls and a rotating coffee can should take good care of grinding the silicon, and to start it up I first went and got what's left of my previously ground homemade silicon. I turned out to have exactly 43 grams of it, which is more than enough for the scale I want to work on, and to turn the silicon sand into silicon flour, I got my steel ball loaded coffee can and tossed it all in. I then sealed up the can and got it onto the mill, which through 2 days of excruciatingly painful sounds made all the silicon into the finest of powders. It really looked like some grey flour and was really satisfying to move around. It was also exactly what I was looking for to make my silicon tetrachloride. Speaking of that, this time I wanted to take extra care in preparing my silicon, and apart from finely powdering it, I also got it into an oven for a few hours to drive out any traces of moisture that would screw up the reaction. While it's cooking, I have to figure out how to put together an apparatus robust enough to safely combine it with chlorine gas. You see, chlorine is one of the nastiest chemicals there are, being very reactive and deadly. Now, combining it with silicon to form silicon tetrachloride isn't as simple as just getting the two close together. The chlorine, apart from having to be generated on the spot, also needs to be bone dry, and it will only feel like reacting with silicon at a comfy 600 degrees Celsius, making the setup require some serious heating. The created silicon tetrachloride gas also has to be simultaneously condensed into a liquid and quickly sealed so that it doesn't just escape into the atmosphere. This whole setup also preferably has to prevent my lungs from getting wrecked, and designing something that fits all these criteria is, let's just say, hard. Nonetheless, after a lot of thinking, I started slowly coming together with something, and after a few hours of tinkering with glassware and my lovely cat's help, I came up with this. This beast of a setup already looks terrifying even though it's not even finished yet. Much like the last time, it is divided into a few parts which serve to create and dry the chlorine, combine it with silicon at high temperature and store the product. Now, each part is a little different than before, starting with the chlorine generator, which has a better valve and will dry the chlorine with anhydrous calcium chloride instead of sulfuric acid, since it's way easier to handle. The silicon tetrachloride synthesis part is also completely reworked, and instead of a trashy glass tube heated with a blowtorch, it consists of my good old electric furnace, which just so happens to have a perfect diameter to house a second wash bottle that will force all the chlorine to react with powdered silicon and maintain an even temperature across the whole setup. The receiver part is also heavily modified with some better pipe fittings and even colder condenser water. Now, instead of letting the silicon tetrachloride into a storage flask where most of it would just evaporate, this genius contraption will pass all of it through some cooled anhydrous ethanol to instantly form TEOS. This will eliminate the whole silicon tetrachloride storage part, which is what really got me last time, and with all my TEOS generated in the ethanol flask, I should be able to easily distill it all off later. I was really eager to try out this whole majestic setup, which should produce silicon tetrachloride and TEOS on a scale never shown before on YouTube. To start it up, I first filled the chlorine generator flask with 150 grams of pool chlorine, or more chemically speaking, calcium hypochlorite, which in combination with concentrated hydrochloric acid, of which I used 500 milliliters in total, should make more than enough chlorine to react with 28 grams of my dry silicon powder. I got it all into the furnace wash bottle, and after that isolated it with some glass wool to later keep more heating. With all the reagents in place, it was now time to set up the tubing, and much like before, I used some PVC. However, on the exhaust of the heated reactor, I installed a more heat and chemical resistant HDPE tube as a safety measure, since you can never trust hot silicon tetrachloride. Just like that, the whole setup was finished, and it honestly looked quite professional, which made me really proud of myself. To start it up, I first preheated the reactor to 200 degrees Celsius in order to fairly dry everything. I then flushed the whole setup with a good amount of argon from my new cylinder, which should get rid of any residual water vapor. It's such a good feeling when you are chemically advanced enough to own an argon cylinder, and using it in a project was a moment I dreamed of for a long time. Anyway, the argon had this funny side effect of carrying tiny particles of silicon out of the reactor straight into my ethanol, making it cloudy, and fortunately they shouldn't interfere with anything. After a few minutes of this argon treatment, the whole setup was ready, and to allow chlorine to react with my silicon, I turned up the furnace's temperature to 600 degrees Celsius. To prevent a potential disaster, I set up this Rubik's Cube supported computer fan blowing on the reactor's outlet as an advanced cooling system, and when the furnace reached the set temperature, I started the chlorine generator. It slowly combines hydrochloric acid with calcium hypochlorite, producing wet chlorine gas, and before going into the reactor, it all gets nicely dried using anhydrous calcium chloride. This dry chlorine then slowly makes its way into the heated reactor, where it's able to combine with the silicon powder, producing silicon tetrachloride. At such high temperatures, it's a gas, so it easily gets pushed out of the reactor into the water-cooled condenser, turning it into this beautiful clear liquid. It then slowly makes its way into the tube leading into the ethanol flask, where it very quickly reacts to form my precious TEOS and a ton of hydrogen chloride. The hydrogen chloride is a gas, so it easily escapes into my fume hood, while the less volatile TEOS stays dissolved in the ethanol. This whole process runs way more smoothly than the previous one, with all the silicon tetrachloride being consumed as quickly as it forms, and much more chlorine reacting with the silicon powder. It, of course, isn't perfect, since a tiny amount of the chlorine nonetheless makes it over to the ethanol, contaminating it a little and potentially reacting with it to form something called chloro, which is actually a mild hypnotic, making this whole thing even funkier than it already is. It fortunately shouldn't be too much of a problem, and even with these minor inconveniences, I am really proud of this creation. It really made quite a bit of silicon tetrachloride, judging from how much accumulated near the condenser, and when the chlorine generation was finished, it was time to collect my product. First, however, I again flushed the entire system with argon to force all the remaining chlorine and silicon tetrachloride to react, and when that was done, I started disassembling everything. This took quite a while and was beyond messy. Now, by far the most interesting thing about the cleanup was the inside of the reactor. The glass wash bottle comically ballooned up and got fused with a piece of glass supporting it. Fortunately, it didn't break and I may still use it for something. The silicon powder looked like it didn't react at all, however that was only because it puffed up during the process and was mostly just some residual silicon dioxide and impurities. After the gigantic cleanup, it was now time to take care of the weirdly clear product of this reaction, which I have to recover from the ethanol. This can be quite easily done by distillation, however, before I took care of that, I wanted to improve my yield a little using silicon tetrachloride from the previous video. It miraculously survived nearly a month in storage and didn't even look that bad. Now, to turn it into TEOS, I could dilute it with something and carefully add it to some fresh ethanol. However, since this is amateur chemistry, I just dumped it all into the product flask from before. Its reaction with ethanol was much more violent than I expected, producing clouds of hydrogen chloride, and without my fume hood it would have been real bad. When the hydrogen chloride storm calmed down, it was time to get my TEOS from this potion of instant sand, and for that I set it up for a simple distillation. After assembling the apparatus, I realized that I somehow made it backwards, since pretty much everyone does their distillation from left to right. It just seemed kind of off, but I guess that this makes this project even more special, and to get my TEOS, I first had to boil off all the ethanol. This was quite easy since it has a relatively low boiling point, and after around an hour pretty much all of it was in the receiving flask. Now, I left the setup unattended for a while, and when I came back, all the liquid in the boiling flask turned into this weird jelly. This made me really scared that all my product decided to just spontaneously decompose into some kind of glass, and this would mean that all the previous weeks of struggle were for nothing. I decided to not even think about that and calmly cranked up the temperature of my hot plate to hopefully boil off at least some intact TEOS. It has quite a high boiling point of 169 degrees Celsius, which made the heating really suspenseful because while the jelly started to mysteriously crack, nothing seemed to come over. I replaced the receiving flask with a smaller one for the TEOS just in case. However, even though the jelly turned white and then black, nothing else happened. I was ready to call this project a failure, but as a last resort attempt to squeeze some product out of the caramelized glass jelly, I wrapped the flask in aluminum foil to keep more heat in and waited. Roughly 5 minutes later, the temperature started rapidly rising and some light yellow liquid started collecting in the receiving flask, which made me just ecstatic. Even though only a small amount came through, this had to be TEOS, and I was amazed that in the end I managed to make it. After disassembling the apparatus, apart from the beautiful product, I was left with this weird black glassy gravel that represented like 70% of my potential yield. Nonetheless, it's very good that I managed to recover anything from it, and now it's time to see exactly how much product I managed to make. It turned out that those few months of work left me with around 39 grams of some weirdly yellow TEOS, corresponding to a whopping 19% yield from the starting silicon with the additional tetrachloride included. This means that the real yield is closer to 15%, which is beyond bad, but at least it's there, and if I were to do this again, I would definitely invest a lot more care into keeping traces of water out of the apparatus. Anyway, even though I have so little product, I wanted to show you some of its reactions. Now, TEOS is like a more well-behaved cousin of silicon tetrachloride, being way less volatile and reactive. It's however not nearly safe enough to work with outside a fume hood, since it can still cover your lungs in sand, only in a slightly milder way. It is also quite flammable, leaving behind a residue of silicon dioxide, and what really surprised me is that it's really resistant to decomposing in water, staying intact even with strong heating. This makes the previous jelly formation even more mysterious. Anyway, now that I have my homemade silicon precursor, it's time to cook up some opals with it. There are dozens of sources on making synthetic opal online, and researching them all was one of the most tedious parts of this project, since I must have spent like 30 hours just wandering around the internet and getting confused by tons of misleading papers or videos. Fortunately, there is some good material on making opals, and I figured that this paper is both in-depth and easy to follow enough for me to use it as the main reference for making my opals. Now, before using any of my very scarce sand-derived TEOS to make opals, I wanted to do at least one practice run without it to be absolutely sure I succeed, since it's basically impossible to make good opals without first testing your setup and learning from your mistakes. The problem with that is I can't make opals without TEOS, and since nobody is eager to sell something so exotic and dangerous, I was kind of screwed. For this reason, I had to put the project on hold for a few months, during which I did even more research and actively searched for anyone selling TEOS, and one day I finally found some. It turned out to just casually appear on eBay for quite a reasonable price, allowing me to buy this 300ml bottle of it. It's kind of ironic how I spent months making a tiny bit of this stuff and one day just bought a bottle of it, but I can now freely test out the opal making procedure without worrying about having to repeat all the previous steps. Anyway, cooking up synthetic opal is a really interesting process, a little similar to actual cooking, and to start I got a small flask with a stir bar and added in 62ml of 99% ethanol, followed by 3ml of distilled water and 8ml of 25% ammonia solution. This makes the basis of the opal making solution, and the only thing left to add now is some TEOS. However, before that I have to fine-tune this solution a little. For that, I put the flask in a hot water bath with a thermometer and turned on strong stirring. The goal here is to get this solution to 60 degrees Celsius and maintain intense stirring, and while everything was warming up, I now have to measure out the TEOS. After getting it out of its very own containment jar, I used a pipette to get 6ml of it into a graduated cylinder, and when the ethanol mixture got to temperature, I used this cute tiny funnel to dump in all the TEOS at once. This made the solution get progressively milkier, ending up looking like some fine cream, and this milkiness is actually my opal in its baby form. You see, in this reaction, tetraethyl orthosilicate slowly gets broken down into pure silicon dioxide by ammonia and water. The created silicon dioxide is in some weird jelly like in almost every other reaction that creates it, but in this one it tends to form some tiny grains. Those grains, being a few hundred atoms wide, then act as seeds for more silicon dioxide to cling onto and gradually grow into these weirdly perfect spheres. Since this whole complicated reaction is done to control the exact size of the spheres that directly dictates the properties of future opal, changing pretty much every factor can heavily influence the final product. In the paper, they figured that they could make a wide range of different sized spheres just by controlling the amount of starting ethanol that dictates how many seed grains grow initially, and in this particular case I added enough ethanol to end up with roughly 270 nanometer wide silica spheres. They should give the opal a green color, and it honestly still amazes me how I can make something so incredibly tiny and precise using only chemistry. Anyway, I left this milky suspension to cook for 2 hours, which should give the spheres enough time to grow completely. I then disassembled the apparatus and was really eager to test out my newly created magic sand, for which I just had to evaporate away the ethanol. I got some of this sphere suspension onto a watch glass, and after letting it dry in the air for a few hours, I was left with this opal residue. Under a certain angle, it actually glowed green, and upon seeing that, I was just amazed. This glow, despite not being too strong, was quite beautiful, and I couldn't wait to see what it will be like when these spheres will have enough time to properly arrange themselves. Now, before I get to settling them and creating the actual opal, I want to have them in some more colors. I decided that I would also test out the synthesis of red and blue spheres, which don't differ in anything from the previous one, except for the amount of ethanol used. For the red ones, I used 53 ml, which by allowing fewer seed grains to form makes the final spheres larger, and for the blue ones, I used 73 ml of ethanol, allowing more seed grains to form and result in overall smaller spheres. Much like before, I dried small samples of the created suspensions on a watch glass, and while the red spheres weren't particularly colorful, the blue ones were just stunning, being nearly transparent for some reason. Anyway, I poured the opal milk from all 3 runs into separate plastic tubes, and now with the silicon dioxide sphere synthesis pretty much nailed, it's time to move to the hardest part of this project, which is making the spheres into opal. You see, having made the correct sized particles is one thing, but forcing them to arrange into a nearly perfect opal structure and making them stay that way is beyond tricky. The first step in doing that is removing the ethanol and ammonia from the sphere suspension, since they otherwise would really interfere with the next step. This is usually done in one of 2 ways, the first one involving just waiting for the particles to settle out on their own, which is really reliable but takes forever, and the second one is much more rad and flashier, featuring the use of a centrifuge to force the spheres out of the suspension. Now, most centrifuges able to handle the amount of liquid I'm working with are really expensive, and there is no fun in just buying them, so to bring some joy to this soul-draining project, I asked my dad to build me one. The thing about my dad's creations is that they are incredibly strong and robust while looking quite rustic, of which my ball mill is the perfect example. Now, this centrifuge, which he built over the weekend for like a quarter of the price of a commercial one, is a real beast, and we keep it in this ancient chicken coop for a very good reason, which is that it could basically explode when it feels like it. To try it out on my opal suspension, I got 2 tubes of it into the opposite sides of the centrifuge pipe. I also used some rusty nails to balance everything out, and after screwing on the caps, the Monster Centrifuge 6000 was now ready. To start it up, I have to progressively insert more plugs into this cable extender, with each one representing a different power level provided by the power supply screwed to the wall. At level 1 this thing is barely spinning, at level 2 however it starts to pick up some steam, and at level 3 it starts screaming ever so softly. Anyway, I left it to beat the hell out of the tubes for half an hour, and after turning it off and waiting a good while for it to stop spinning, I recovered the tubes and this thing actually worked. I mean, the separation wasn't perfect, and considering the risk factor of running this thing, I will probably resort to the more family-friendly method in my future runs. However, this doesn't mean that the centrifuge is bad, and my dad did a really solid job. Anyway, now that I have these small packs of concentrated silicon dioxide spheres on the bottoms of the tubes, I can continue to the next step in making my opals. I now have to resuspend them in water, and I did that by spinning down the last tube, off-screen adding a few milliliters of distilled water into it, and then using this new suspension to resuspend the previously created opal packs. They all broke down really quickly, and this whole step left me with a very concentrated suspension of multicolored silica nanospheres in water. This special milk is really close to becoming a hopefully very colorful opal, and I now have to settle out and dry the spheres. This can be done in pretty much every container, however I ultimately decided to use this silicone chocolate mold. It should make the opals have a cool round shape and allow me to make a few at a time. Now, to make the first official amateur chemistry opals, I poured all my silicone cream into 2 of the molds. I now have to leave them undisturbed for a long time, in which the spheres will hopefully arrange themselves correctly and the water will slowly evaporate. Suspiciously, after just 5 days, everything seemed bone dry and the opals turned out to stick to the sides of the mold rather than settle into a nice opal pack at the bottom. This was quite disappointing and definitely not what I expected, and I think that this uneven drying was caused by too much ethanol still being present in the suspension, making it dry too fast for the spheres to settle properly. This was both bad and good, since now I know how to not waste my homemade TEOS. Anyway, these quote-unquote opals were also beyond delicate, crumbling upon the lightest touch. They also somehow adhered to the silicone mold, which is another problem I will have to fix later, and this whole tutorial opal making process left me with some white, crumbly pieces of what felt like chalk. Fortunately, it's not just any chalk, and since it's made of millions of microscopic spheres, I had some hope I could still turn it into opal. If I found a process that could both make it transparent and harder, I would be satisfied with the result, even though the opals would be really small, and I actually had one idea in mind. In one of my weekly research sessions, I stumbled upon this video that claimed that you can easily turn some white and crumbly synthetic opal into a really beautiful gemstone just by heating it in a furnace. I was wondering why I didn't stumble upon it before, since this would fix all my problems, and with a new dose of confidence, I went and got my trusty furnace. It's cool that I get to use it again in this project, and the guy in the video called for heating the opal first at 572 degrees Celsius for 8 hours and then at 835 degrees Celsius for a day. These temperatures seemed kind of random, since silicon dioxide's melting point is far above both. However, since I don't really want to melt these spheres and just lightly glue them together, this still seemed plausible. I loaded a few pieces of my raw opal into a ceramic crucible and got it into the furnace. I then set the temperature to 535 degrees Celsius, since this furnace displays a temperature around 50 degrees Celsius lower than it actually is. When it warmed up, I held it there for around 8 hours and then cranked the furnace up to 780 degrees Celsius and held it there for exactly a day. I then let it slowly cool down over the course of another day, and when I recovered the crucible, the opals were the same as before. This was quite suspicious, but I still thought that I was just doing something wrong, so I decided to fire the opals a few more times. By a few, I mean like 10, each one with different temperatures and firing times. I even bought a microwave kiln and tried firing the opals with it, which, while actually melting them down, didn't even make them transparent. At this point, I realized I just got willingly scammed and for the 1000th time learned that you can't trust random people on the internet. Now, while that guy definitely made some good silica spheres and can beautifully cut opals, he definitely didn't manage to make an opal this pretty and transparent from them using just the setup he showcased, and upon watching the video more closely, I realized that quite a lot of things from it don't make sense. It's really sad to spend so much time trying out something that can't work, and at this stage of the project I was feeling pretty unsure if I would be able to make anything resembling real opal. Nonetheless, I figured I was way too deep into the opal rabbit hole to stop now, and with everything before the firing sorted out, it was time to break out my homemade TEOS and finally have a try at making opals from dirt. Making the spheres turned out to be a walk in the park, and using pretty much the same setup as before, I again prepared 3 batches of silica nanospheres, this time on a 2 times larger scale. This consumed pretty much all my dirt-derived tetraethyl orthosilicate and left me with these 3 half-full bottles of 100% natural opal milk. Much like the last time, I dried small samples of each one and they looked even better than before. I mean, the green one was just stunning with this very opalescent spot in the middle, the blue one also seemed even prettier than before, and only the red sample still looked white. Anyway, with some quality silicon dioxide spheres acquired, now it's time to remove as much ethanol as I can from them, and since I now know that the centrifuge isn't the best option for that, I just put all 3 bottles onto a rack in my attic and left them there. Over around 2 weeks, gravity slowly settled them out, forming these thin and already quite opalescent layers on the bottom of the bottles. The blue spheres being the lightest ones settled out the last, and when the ethanol in each bottle looked clear, I very carefully transferred them back into my lab. This whole settling step wasn't actually nearly as much of a pain I imagined it to be, and now to get rid of the ethanol, I didn't want to just pour it out because I would probably lose a lot of the spheres. After some tinkering, I came up with this advanced system I proudly call the Sucker 3000. Using a vacuum pump and a modified pipette, it can very easily and cleanly suck out all the ethanol from the bottles with minimal disturbance of the opal layers. I was quite surprised by how nicely it worked, and now with almost no ethanol in my opal concentrate, I could freely add a small amount of distilled water to loosen it up and transfer all the spheres into this bottle. It's amazing how powerful learning from your mistakes can be, since this step went really well, and now to dry the spheres I had to tweak my silicone mold a little. I thoroughly cleaned out all the previous opal residue, and after a brainstorming session I figured out a better way to dry my opal. This new process heavily relies on this bottle of vegetable oil, which when applied to the mold makes it quite sticky, allowing some saran wrap to easily adhere to it. Since the oil won't evaporate or solidify, the opals will have some freedom to change shape as they dry, which should prevent cracking and allow the water to evaporate faster. This whole thing seemed just genius, and to test it out I filled all the saran wrap covered molds with my opal water along with 4 more normal molds for comparison. This nicely used up all the sphere suspension, and with the mold ready I got it onto my attic rack to dry. It took roughly a month, and when I got it into my lab, I was just ecstatic. It turned out that my vegetable oil idea was a smashing success, with none of the 4 opals made with it cracking at all. Compared to all the ultra-complicated industrial drying methods, this was just a perfect amateur chemistry moment. I carefully removed all the opals from the saran wrap, and while one unfortunately cracked, the other 3 were just fine. Now, even though the unoiled opals also dried alright, they again got stuck to the mold and all cracked upon the slightest touch, which proved the superiority of my drying method even further. These opals were already much better than the previous ones, with the oil-dried ones being surprisingly dense and kind of hard. They also already had quite a bit of surface opalescence. Under a flashlight they were weirdly yellow, probably due to the tiny amount of impurity in the starting TEOS, and I was honestly already quite pleased with how they turned out. The less pretty opal chunks were also quite alright. For some reason they were much softer than the other ones, behaving exactly like chalk. Anyway, I got both of my opal grades into those completely not suspicious Ziploc bags, and now it's time to fire them. It definitely won't make them transparent, but during my previous testing I found that above about 900 degrees Celsius they acquired quite a bit more hardness and a little more color. For the first firing, I didn't feel quite safe enough to use one of the intact big opals, so I loaded the best lower quality one into my crucible and got it into the furnace. I then proceeded to heat it up to the aforementioned 950 degrees Celsius and held it there for 2 hours. I then allowed everything to cool down overnight, and in the morning I got the crucible out. The opal unfortunately cracked quite a bit, but as I expected was much stronger and way less crumbly. Since I didn't want to stop at some homemade opal gravel, I figured that maybe one of the better opals would somehow survive the heat treatment. Much like before, I loaded it into the crucible and put everything into my furnace. However, this time as an extra precaution, I set the furnace to 80 degrees Celsius and left the opal to cook like that for a day. This extra heating step should force any remaining traces of water out of the deepest parts of the opal without cracking it, which hopefully will make it withstand hotter temperatures better. After the day was up, I cranked the furnace temperature to 950 degrees Celsius and held it there for 3 hours. I then again left the furnace to cool overnight, and when I came back it was time for the moment of truth. I quite nervously got the crucible out of the furnace, and upon tilting it I was just out of words.
Yeah.
It turned out that my big homemade opal withstood literal hell in perfect condition, having no cracks and being strong enough to resist being used as chalk. It also glowed way prettier than before, which was just amazing, and after nearly a year of chemical struggles, I am proud to say I made an opal from dirt. It's definitely not perfect, having a very rough shape and not being transparent, but just how cool is it that it was once the literal ground. It also weighs nearly 600 milligrams or 3 carats, which is quite a bit, and after looking at it for like an hour, I felt a great deal of satisfaction. Now, about a month after I made it, I started writing the script for this video, being sure that I did everything I could to make my homemade opal as pretty as possible, and when things couldn't get any better, they suddenly did. You see, the only thing that would make this project even more perfect than it already is would be making this opal transparent while preserving its opalescence, and after figuring out that the YouTube video lied, I kinda gave up on it. Making transparent synthetic opal turns out to be a very difficult process even in the industry, and doing it in my parents' garage seemed kind of impossible. One day, however, while randomly surfing through silicon dioxide's Wikipedia page, I noticed something I hadn't really paid much attention to before. This little goober called refractive index really stuck out to me for some reason, and after reading some more about it, I experienced chemical enlightenment. You see, the refractive index of materials is a property that dictates how they reflect light. When its value is different for two adjacent materials, light passing through them will get bent, and this is what causes my opals to be opaque. Since at the atomic level they are a forest of silica spheres with quite a bit of air in between, the light jumping from one medium to another gets reflected all around the place. If the space between the spheres was however replaced by something with a very similar refractive index, light should freely pass through the opal, making it transparent and hopefully preserving its opalescence. Upon coming up with this wild theory, I was really eager to try it out, and I first had to find something with a refractive index nearly identical to that of silicon dioxide. After doing some more research, I found that this liquid called chlorobenzene is nearly a perfect match with a refractive index really close to silicon dioxide's and quite a cheap price. I bought this 1 liter bottle of it specifically for this project, however, after dropping a piece of my fired opal into a small beaker of it, nothing really happened. I mean, the chlorobenzene definitely got sucked into the opal alcohol since a lot of bubbles escaped from it, but other than that, it didn't do anything remarkable. At first, I thought that maybe this idea was too wild to actually work, but after a few more hours of research, I found that synthetic opal for some reason has a different refractive index than pure silicon dioxide. This meant that I had to use a different liquid, and since I didn't have anything pure with the required refractive index on hand, I reached out to the one and only ChatGPT for help. It suggested using mixtures of two liquids with different refractive indexes, one of which was a combination of ethanol and benzyl alcohol. These alcohols are relatively common in a chemistry lab and have the benefit of being quite non-toxic while also having a low volatility, both of which should make the final wet opal quite family friendly. Now, to achieve the right refractive index, ChatGPT called for a 30-70 mixture by weight of ethanol and benzyl alcohol. However, since I don't know the exact refractive index of my derived opal, I decided to find it out experimentally before doing any large-scale testing. To do that, I got 5 glass vials and labeled each of them using a marker. I then drew this very scientific table with the amounts of each alcohol I will put in the vials. Vial number 3 will be the default 30-70 mixture of ethanol and benzyl alcohol by weight, and all the other ones will deviate from this a little to see what effect it will have on the opals. To precisely prepare the alcohol mixtures, I got my milligram scale and using pipettes added the correct amount of each alcohol to all the vials. When I was done, I was left with 5 almost identical vials, each containing exactly a gram of the customized refractive liquid. The first one was also weirdly pink, which is due to this one godforsaken dye I made like half a year ago and still can't get off my glassware. Anyway, to find out which one of these solutions has the right refractive index to make my opal transparent, I dropped in little pieces of it left over from a previous firing. They all absorbed the alcohol solution quite quickly, and each one turned out to look surprisingly different. You see, the first vial with the pink solution didn't really change the opal that much. However, by vial 3 it started to become kind of transparent. Now, by far the most impressive result I got was the last vial, in which the opal completely disappeared. I mean, this was exactly what I wanted to achieve, and I was just amazed that this whole thing has actually worked, and achieving an opal this transparent means that the refractive indexes of it and the alcohol solution are pretty much identical. Now, since I couldn't really see much color in such a small sample, I decided it was time to disappear the big opal. For that, I got this small vial with a Teflon tape coated thread onto my scale and mixed up some more of the alcohol solution. This time I made it on a 10 times bigger scale with proportions resembling the solution from the last vial, and when it was done, it was time to throw in the opal. At first, it didn't really seem to get any more transparent, but since it's way bigger than the previous one, I allowed it to soak in the solution for quite a bit more time. After about 2 hours, no more bubbles were coming from it, and when I capped the vial and shined a light on it, I was just in awe. I mean, I could spend another 5 minutes describing the beauty of this thing, but I think that the footage speaks for itself way better than words ever could. It's a really great feeling when months of your work finally pay off, and my homemade opal is the perfect example of that. It turned out almost completely transparent, only with this small opaque area on its bottom which has a slightly different refractive index than the rest of the opal for some reason. It fortunately does nothing to alter the play of color of this thing, which remained completely intact, and I would even say that the alcohol solution enhanced it. What's also really cool is that it's only visible from a certain angle, and otherwise the opal just magically disappears into the solution. It also looks very nice under the sun, and I really couldn't have dreamed of a better outcome for this year-long project. In retrospect, putting up with all those painful and toxic reactions along with a great deal of research and experimentation was well worth it, and it's projects like these that teach me to not give up too easily and make me love chemistry even more. This whole journey of making a gemstone from the ground was one of the longest ones I've ever gone through on this channel, and with this video being over 40 minutes long, it officially makes it my biggest project to date. Now, to share a piece of the awesomeness of homemade opals with you, I whipped up some more of them using the leftover store-bought TEOS and plan to later do a giveaway and maybe even sell them if enough people are interested. I also plan to combine all the videos in this series into a single gigantic one for an even more in-depth experience, and I figured that I will do the giveaway when I post it, probably in a few months. Also, in terms of my future projects, I am actively working on things like taking photos using Rust, making glow-in-the-dark powders, sodium borohydride, and recording many shorter projects. I also plan to come back to recording shorts and finally set up the second channel for more behind-the-scenes content, so stay tuned. For now, I want to thank you all for being here. It's you who make this channel possible and motivate me to keep recording all these videos, and if you enjoyed this one, you can like it, share it with a friend, and subscribe to my channel. If you would want to further support my work and gain access to a lot of cool exclusive videos like my official lab tour, I invite you to join my Patreon. Also, a big thank you goes to all my amazing patrons for their support and allowing me to have the resources necessary to complete all my projects, and see you guys in the next video.